Programmable logic controllers, or PLCs, are like the brains of modern factories. Imagine a computer that can control machines, but instead of a keyboard and mouse, it uses signals from sensors and buttons. That's a PLC in a nutshell. PLCs are essential for automation, helping factories work faster, safer, and more efficiently. Before PLCs, factories used complicated systems of relays for automation. Relays are electrical switches, and using them for complex tasks was like building a giant puzzle with thousands of pieces. It was time-consuming to wire, difficult to troubleshoot, and nearly impossible to change quickly. PLCs were invented in the late 1960s to replace these cumbersome relay systems. They offered a flexible and programmable solution, revolutionizing industrial control. A PLC system consists of several key components. The central processing unit, CPU, is the brain, making decisions based on the program. The power supply provides the electricity to run the system. Input modules receive signals from sensors, buttons, and switches, telling the PLC what's happening in the real world. Output modules send commands to motors, lights, and other actuators, controlling the actions of the machines. PLCs are used in a wide range of industries. In manufacturing, they control assembly lines, packaging machines, and robotic arms. Think about a car factory where robots weld parts together. A PLC is likely controlling the timing and movements of those robots. PLCs are also used in other industries like traffic control systems, water treatment plants, and amusement park rides. Section 5. Programming the PLC, a simple guide. Programming a PLC might seem daunting at first, but it's simpler than you might think. One of the most common programming languages used is called ladder logic. It uses symbols that look like rungs on a ladder, making it easy to understand the logic flow. Each rung represents a specific action, like turning on a motor or opening a valve. Section 6. Input and output, the language of PLCs. PLCs communicate with the outside world through inputs and outputs. Inputs are signals received from sensors and switches, providing information about the system's state. For example, a sensor might detect if a conveyor belt is full, sending a signal to the PLC. Outputs are commands sent from the PLC to control actuators like motors, valves, and lights. The PLC uses the input signals and the program logic to determine the appropriate output signals. Section 7. Ladder logic. Visualizing control. Ladder logic is a graphical programming language that uses symbols to represent electrical circuits. It's called ladder logic because the program resembles a ladder, with two vertical rails and rungs connecting them. Each rung represents a specific condition and its corresponding action. The left rail is considered the power rail, and the right rail is the neutral rail. If the conditions on a rung are met, the logic flows from left to right, activating the output on that rung. Section 8. PLCs, the backbone of modern industry. PLCs are crucial for modern industrial automation. They allow for precise control, increased efficiency, and improved safety in various processes. By automating tasks, PLCs free up human workers from repetitive or dangerous jobs, allowing them to focus on more complex tasks. This leads to higher productivity, better quality products, and a safer working environment. Section 9. Conclusion. Embracing the future with PLCs. As technology advances, PLCs will continue to play a vital role in shaping the future of industries. Understanding the basics of PLC programming is becoming increasingly valuable in today's job market. With their ability to control complex systems and improve efficiency, PLCs are essential tools for anyone interested in the world of automation and industrial control.